polynomial. If I want to apply a complex polynomial root finding to f of x, which was a polynomial with real coefficients, then I can only approximate its roots, and I want to go from approximate roots of that to approximate roots of the Quaternion polynomial. How do we do that? This is a theorem that took me a while to prove it, but once you see it, it's easy, but it's not straightforward really. Suppose that for some complex number theta, the function f of theta is less than or equal to epsilon squared. Remember that f of x was p of x times p bar of x. So suppose we have achieved the approximation to a zero to within epsilon squared. Then you define these two numbers, q and q prime. If p bar of theta is bigger than epsilon, then p of q is less than epsilon. If p bar of theta bar is bigger than epsilon, then p of q prime is less than epsilon. If p bar of theta and p bar of theta bar are both less than epsilon, then p of theta and p bar of theta is less than square root of 2 epsilon. So this means we can approximate the roots to, if I want to approximate, the function to within accuracy epsilon, the p, it requires approximating f of x to accuracy epsilon. You may say this is a drawback because you have to obtain more accuracy in f. And this is true. But at least one thing that we know is that we can apply complexity results, such as those of Tan and Reich, to complex polynomial root finding and apply it to Quaternion polynomial root finding. Bounds on zeros of Quaternion polynomials. Suppose that p is a Quaternion polynomial, consider f of x. Then for each root of p of x, there is a root of f of x, having the same modulus. Conversely, for each root of f of x, there is a root of p of x having the same modulus. So this means that if I want to bound the roots of a given Quaternion polynomial, I might as well go to f of x. In fact, you do find in the literature, people try to find bounds, but they seem to not use this connection. For instance, even in 2009, there is a bound, direct bound on p of x. And really, what this result says is that to have effective bounds on the roots of p of x, you must have effective bounds on the roots of f of x. But to compute f of x is no big deal. We just need a pre-processing of multiplying coefficients. It can be done, of course, efficiently. In fact, bounds on zeros of polynomial are nice and not so easy to obtain. And I happen to have a infinite family of bounds on the zeros of a complex polynomial, defined in terms of its coefficients. And as Eugene, who was my PhD student, proved in 2006, these bounds asymptotically converge to the tightest annulus that contains the roots. And they are efficiently computable too. As an example, if for m equal to 2, one of the bounds on the zeros of such a complex polynomial is this. For m equal to 3, we compute a 2 by 2 matrix and range over these indices, and that gives a bound. And for m equal to 4, we need 3 by 3 matrices. In fact, McNamee, who has a book on polynomial root finding, he has done a computational analysis of even this bound only, with more than 45 different bounds in the literature, and he found this to be more effective than those. If you go to m equal to 5, you should even get a better bound. The composition of a Quaternion polynomial. We say a monic polynomial, Quaternion polynomial, is a type 1 polynomial if it's either 1 or it factors as a product of terms of such, where Ri and Rj are from different conjugacy classes. A monic quaternion polynomial of degree n2 bigger than or equal to 0 is a type 2 if essentially it factors into the product of characteristic polynomials raised to some powers. And here is a theorem that is more precise than other theorems I've seen in the literature. You take a monic quaternion polynomial, it factors into the product as a product of 3 polynomials, where P1 is a type 1, P2 is a type 2, and P0 is a polynomial of degree bigger than or equal to 0, with the property that it has no roots in common with P of x. But that for each of its roots, there is a conjugate which is a root of P of x. So, you may have this weird situation in the case of quaternion polynomials, where you get a part that contributes nothing in terms of zeros, but its zeros have in turn a conjugate, a distinct conjugate that's the root of P. Number of zeros, if a polynomial is of degree n bigger than or equal to 1, it consists of n1 points in H counted with multiplicity and n2 spheres of zeros centered as such points satisfying this bound. If P is not root deficient, I say it's root deficient if P0 is of degree bigger than 1, bigger than or equal to 1. So if it is not root deficient, then you get this exact. Location of zeros, when we can understand polynomials, I think quaternion polynomials, if you can understand where the zeros could be, how they could be, and whether you can construct a polynomial with the given zeros. In the complex case, it's very easy, right? You want to have a polynomial having zeros, you just take the product, a given set of zeros, you multiply it by products of the term x minus, the complex. But what do you do in the quaternion case? Anyway, first, the roots if the roots are simple, then they can be located anywhere in R to the 4. But the spheres are all centered on the x1 axis. It's unfortunately hard to visualize the zeros of the quaternion polynomial in dimension 4. Quaternion polynomials with prescribed zeros. Here I have a procedure that can construct a polynomial with prescribed quaternions. And this is interesting from point of view of polynomiography. I skipped that. Taylor's theorem and iterative methods. Derivatives in the quaternion case are not so easily definable because you have to go to Jacobians of the map. These dynamical systems theory doesn't really apply. But nevertheless, we can define a formal derivative. And we have this theorem. It's Taylor's theorem over quaternion can be proved. Maybe the importance of this theorem or this expansion is that it is valid since x is assumed to commute with the coefficients. However, it does not necessarily hold for specific values of x. See, this expansion doesn't hold for if you plug in x equal to c, it holds. But it approximately holds for points which are close to c. And this means that you can, in a way, define things such as Newton's method. This expansion is valid as a polynomial over quaternions. And given an initial seed, you can define iterations, Newton's method like this. You have to multiply it in the left for it to mean something. Okay, multiplication on the right may give you something meaningless of the inverse. And one can show that if the root, if there exists a neighborhood of C such that the fixed point iteration is well defined, first there is a neighborhood, and if C is a simple root and x0 commutes with the coefficients and with C, then the fixed point iteration, assuming convergent to C, will have a quadratic rate of convergence. So in a way, we can have Newton's method. And you don't find really a lot on such things. Even Halley's method, derived Halley's method, third order method, in a way. And it's more complicated to derive this than the complex case. Homogeneous linear recurrence relations. How do you solve a homogeneous linear recurrence relation where the coefficients are that? This is a very special kind of initial conditions. I call it basic initial conditions. Characteristic polynomials can be defined as usual and what I call negative reciprocal. Characterization of solutions, you have, suppose that you have a quaternion polynomial q of x, or characteristic polynomial, which is not, root deficient, and with the property that no three of them belong to the same conjugacy class. Then there exists a unique set of alpha i's so that it can be represented as such. Okay. I mean, we don't get this for free. It's not just saying, okay, we do it in the complex so we can get it in the quaternion case. And in fact, I ended up to prove that. I discovered this nice result in 1999, that necessary and sufficient conditions that a linear system with a van der Waals coefficient matrix has a unique solution is that the so-called double determinant is non-zero. And this is true if and only if no three of them belong to the same conjugacy class. So it's nice to have that characterization. And if you, just as you know, the usual case, complex case, if you multiply this reciprocal, it converges not to the unique dominant root, but to a conjugate of that. Okay, so this was, you know, like, this is not bad because this is a Bernoulli extension, sort of Bernoulli method over the quaternions. And the nice thing is that once we know such a thing, which is a conjugate of the dominant root of Q, then we know we can use Niven's algorithm. Because Niven's algorithm, remember, says if you know the norm and trace of a root, then you can determine a root. General solutions also apply. So let me just skip over these. And quaternions. Polynomiography in 2D, 3D, 4D.
Wow.
How do we do Newton?
4D, wow.
Yes. So this is not so easy to do. If you look in the literature, as early as maybe like late 80s, you see some playing with Julius's of quadratic iteration. But they don't say very much. In fact, just as the Mandelbrot set itself doesn't capture polynomial root finding in the complex, neither does quadratic iterations in over quaternions describe properties of what happens. It's much tougher, but anyway, there are methods. I have sort of methods now that I can define a Newton's method and Halley method, etc. I can iterate, and in this category we can simply apply any polynomiography to this method, to this function. And another category is the following. Imagine you take a quaternion Q and you define complexify Q by taking its complex conjugate. Then consider Newton iteration and the following iterative algorithm. Given a current iteration, we compute the next iteration as we apply Newtons and then we complexify. We put it on the plane. So this way we can see what's going on in the plane. So we can look at the orbits and see what happens to them. There are lots of tough questions about their convergence. Similarly, we can define Halley's method. The third category into the is using a hybrid algorithm, using the connections between P and f of x. And suppose that we define Newton iteration with respect to P of x and f of x by n sub p and n sub f. Then, given a current iteration xk, assuming this is not yet satisfying given tolerance, we take yk to be the complexifying the Newton iterate. Then we lift yk to a quaternion by that version of the fundamental theorem that we have. So we can go from 2 dimension to 4, see what's happening, and then bring it down here. And then there are other approaches. So if otherwise we do it like this. So there is also in 3 and 4. So maybe I will skip this. And this brings me in a way, I think, close to the end, except that, as I mentioned earlier, if I have time for 5 minutes, or maybe less than that, I can tell you what I call a geometric modulus principle for polynomials, complex polynomials. May I? Or do I have time?
Hang on, next time. Next year.
Okay.
Thank you. But I will be glad to answer questions in private. Thank you. That was really beautiful. So you have a few things that